So how does this go on? Oh, yes. What is it?
There it is.
Now I have them both. Okay. All right. Is this working? Hello, everyone. My name is Arthur Franz, and I'm an independent researcher from Germany, and I'm working on incremental compression, which is supposed to be a faster way to do universal induction, and I'm going to present a theory about it to you today. And so the motivation is that every intelligent system has to try to construct short models and descriptions of the world given its observations. And the main principle is Occam's razor, as everybody basically accepts. We want to find concise and parsimonious models of our data, and as Solomonov's universal induction has shown, it has the highest chance to be predictive of the future development of the environment or other parts of the environment, and it reduces overfitting, and it has actually the largest chance to be the right description of the structure of the environment or whatever we want to describe. So the problem is how to build a general AI that finds good descriptions of the world in a wide range of environment. And the only general thing we have is variants of universal search like Levin search, which executes programs which are coded as binary strings and ordered by the length. Execute them one after the other until one of them produces the string that you want to compute. And as we know, it's very slow, of course, and goes due to the order of the length of the program. And therefore it's impractical, and we need to find better ways to do this. And current efficient approaches are, on the other hand, not general. So like PCA, deep learning can add many more that try to somehow, deep learning, you have many layers with ever decreasing number of neurons, which can be understood as dual compression. So the big question is how to make things practical while still staying general. So in practice, describing stuff is incremental. We have objects, they often have features like size, shape, and color. And usually when we describe object, we just describe one after the other. We specify the size, and then we map the original description of the object. For example, it's described as a binary string, to everything except the size. It's like a residual description, which I will call parameters. And then you start specifying the shape and map the residual, then it's everything except size and shape. And you keep going specifying the features until you have found the description of the full object. Intuition tells us that those features are often independent properties, and if the features are described concisely, the full description will be concise as well, like the length of the shortest description, maybe the sum of the length of the descriptions of the features. Well, this is just intuition, and I have put that in a mathematical theory that actually confirms that, proves that, and it will turn out that it will result in an exponential speed up compared to Levin search while still staying general. So let's jump into it. So what is a single compression step? First, we have a string as a binary string that we want to compress, that we want to find a short description of. Remember that finite strings and map there's a one-to-one map between finite strings and Turing machines. So the task is to find two functions for Turing machines, f star and f prime star, that are inverse of each other. So the descriptive map f prime will take x and compute the parameters, and then the feature, what I call the feature, is a function that takes the parameters and computes x again. And the new description of x will be the feature plus the parameters, which we require to be shorter than the original string x. So we have the original description and have reduced the length of the description. So we have first the string, and we have a little bit a shorter description than the length of x. So then we keep going and compressing further and further. Here you see the full compression scheme. First x, find the first parameters, and then you treat the parameters as if it was x and keep compressing it further and get smaller and smaller, and you end up with having a set of features, which are the red ones here. And the question is, of course, is this of any use? But first, I want to give you an example to make it more understandable. So let's say you have a string. We have 1, 1, followed by 0, 2 ones, 3 ones, 4 ones, 5 ones, and so on. Simple string. And the feature f1 may be a function that prints m once and attaches a 0. And as an input, it takes the parameters p1. So it first prints 1, 1, then 2 ones, then 3 ones, 4 and 5 ones. And once you have that, you have done the first compression step, and then you take the parameters and keep compressing them. So the feature f2 starts with 1 and counts up and you arrive at 1, 2, 3, 4, 5. And this is an example of a 2-level compressible string. So those exist actually in practice. So what do we get from it overall? What I have managed to prove is that first, if you do that and choose the shortest feature and shortest descriptive map, the length of the feature will be incompressible. Sort of makes sense. And the other important result is that the information that is inside X is being partitioned between the feature and the parameter. So they both do not overlap. They do not have information that it contains in the other one. And they also do not describe more than X. They partition it exactly. Mathematically expressed that the Kolmogorov complexity, the prefix complexity of X, is the sum of the length of the feature plus the complexity of the parameters. So we have this, we have the string, and we have sliced off a piece of information. And when we can, and what is left, we keep compressing independently of that. And why does it work? The proofs are in the paper. Of course, I cannot go through them here, but I can try to give you some intuition why it works. Suppose the feature and the parameter contain common information, but then you could make the feature even shorter. It doesn't need that information, so it takes it along when computing X. If the information is inside P, it doesn't need it itself. That's the intuition behind it. And the big question is, is this of any use? What do we get from it? And if you keep doing that, then compress the parameter, the next, you will end up representing the Kolmogorov complexity of X as the sum of the lengths of the features. This is one of the main results here. Because a priori, it's not clear if you use that kind of scheme in order to arrive at a short description of an object, that you will arrive at the shortest one. Maybe you will not, right? A priori, it's not clear. But I have proven that you do, up to additive constants you have to add here. What else can we derive from this? Since the feature and the parameters are independent, if you then keep compressing the parameters, all the next features here, f2 until fk, will contain only the information about P1. And that means it will also independent of F1. And this implies that the features are all independent of each other. They do not, the mutual algorithmic information between arbitrary feature, two features is 0. So, yes? 5 minutes, yes. So, what we conclude here is that that the set of features is an orthogonal basis of X. Orthogonal because they don't have common information, and the basis because it's complete. They completely describe the string. So how efficient is this? So from that formula, we see that the average length of the feature is much shorter than the Kolmogorov complexity. And if we use something like Levin search and try to loop through all programs to find the feature, the number of programs we'll have to go through will be much smaller than the one using Levin search, where you have to go through 2 to the power of k of x programs. So that's good. Finding a single feature is much faster as using Levin search for usually in a non-incremental fashion. So what about the descriptive map? Because you have to search for it too. And what I have found is that the length of the descriptive map is smaller than basically the logarithm of the Kolmogorov complexity, up to some small terms here, which is very small. And if you also search for the descriptive map, it will take you time 2 to the L of 2 to the length of the descriptive map, and that's roughly the Kolmogorov complexity. So that's how many steps you need in order to find it, which is not a lot, right? And it's, again, much smaller than the non-incremental Levin search. So I will go through the proofs here. So what do we gain in terms of, we have that approach now that actually finds the shortest description in an elegant way. Can we actually say that it will be faster than Levin search? So how efficient is this? Suppose we look for the shortest feature in descriptive map in a combined fashion, so that we need 2 to the power of sum of the lengths. And if we insert the bounds that I have derived, you'll arrive at that expression for the descriptive map. And then you do the same at every compression step. So, and since once you have found the first feature and looking for the second and third and so on, you don't have to track back and update the first. The time complexity just goes linearly with the number of compression layers that you have. So it's just the sum of those guys that you had here. And let's compare, so this is then roughly the time complexity of incremental compression. Let's compare it to non-incremental search. Well, recall that we have that formula here. And this is non-incremental search. And if you insert that, it becomes the product of 2 to the power of L. And comparing that to incremental search, it takes much longer time, much more time. And because usually for most combinations of lengths of fixed sum, this inequality is generally valid. So what we have that incremental search is much more efficient than non-incremental one, although we have to keep in mind that the features are, the whole mathematical proofs are made for prefix complexity, which is incomputable, of course, but so the comparison is only half valid, but chances are that in practice it still works, and in fact, what happens in practice, and I have already demonstrated in my last year's AGI publication, I have implemented general incremental compression, and in at least some variant of it, and it does seem to work without many difficulties. So how realistic is this? We of course want to at some point head towards realistic applications and to use that, not just doing theory. So one possible prospect is to find a better IXE approximation which can now do tic-tac-toe and Pac-Man and all those different games. Maybe we can go further beyond that because we have an additional speed up here. And another possibility is 100-bit worlds, which is just simple worlds made out of line drawings, triangles, rectangles that do something. And if they move about, people actually often interpret, like there are this famous Heidel and Simmel videos where a big circle chases a small triangle and we interpret it richly. So we can actually build rich worlds. I have more. Okay. And try to apply that. So then I skip future work. Well, there's stuff to do with that too, because we can try to compress. We can try to take the whole string and compress one part of it and then another part and then another part, and that may increase even more speed up what our present algorithm. So I summarized that the incremental compression promises to be fast, and while still studying general, and much closer to a practical application than non-incremental universal search. Thank you for your attention.